This is great. We have trying to understand this with.
This is our the nitrogen vacancy area. So you actually get to hold my diamonds. So I've got actually 3 diamonds in cases here. This is I can pass that around. So that one's actually you see it inside here, right? This is a brilliant cut diamond, and for the reason I have it actually is this is what goes in the diamond anvil cells. So you actually want those facets to actually transmit the pressure. But I carry this one with me for these demos because people expect that's what a diamond looks like. Exactly.
And then we get the boring.
The boring ones, yeah. I actually
How many carats?
Yeah. But this one, I've handed this one to people before from like DOE, and they're like, "What is it? It looks like a piece of glass." So this one is an optical grade diamond. It's got very few impurities in it, and that's usually our starting point with, actually making nitrogen vacancies. You start with a blank slate.
And that's the little chip you had about like that was $2,000 or something like that.
So
right?
this one's about $1,000. So I got my eyes on you guys.
This $2,000, this one?
1,000.
That's very small.
It's not too shiny because it's not cut at angles.
That's right. I mean, it looks like a glass plate because light really transmits through. You're not really refracting anything, and
So small.
that's right. That's right. That one is actually also a lab grown. But that one is specifically it's specifically cut for high pressure applications. So it's got all the facets. That's right. That's right. And this has a lot of nitrogen impurities. So you actually see the yellow coloring to it. And so that's actually the ones that we use. If we irradiate that with electrons, you can make a bunch of vacancies. You anneal it, and then you can make a nitrogen vacancy diamond. So that's actually where this glass slide comes in. So this glass slide, I have one of the high purity diamonds on it. I glued them down, pardon the glue. And we have a purple diamond. So a purple diamond is actually a diamond that started out as that yellow diamond. We irradiated it, annealed it to then migrate the vacancies to the nitrogens, where it's actually stable and it makes nitrogen vacancies. So the next part of this is actually we can see photoluminescence using my little demonstrator here. The way this goes is that I've got, someone might have stolen one pair of glasses. I've got laser glasses. So this will block out the green light, but not any red light. So you can start over here. We'll go a few at a time. Oh, here's one more. Three at a time. So what we can do is first I put this laser, you can see that it blocks out the green of the laser. And if I put this onto the optical grade diamond, the high purity, which is where it's at right now, you can see that it's very boring, right?
I don't really see anything.
And you're not supposed to. Now, if I put this on the purple diamond,
Yeah, see red.
the story changes. Now, this is part of the solid state effect, right? Green light is higher energy than the zero phonon line. So next glasses, pass them down. Oh yeah, more. We got more.
But
There we go.
oh yeah.
So it glows like a beacon because of all the NBs.
But my question is, when I was reading glass, it was red, and then I took it off, and now it is green.
Well, that's because the green mostly overwhelms it. That actual effect, and that's a matter of the quantum efficiency of how much it's absorbing versus emitting. And so it doesn't perfectly absorb green, but it will emit a lot of red. I think we got everybody now, right?
Yeah. Now green. Do you see red? Nice. Do you see red?
Through the glass.
Yes,
Oh,
right.
yeah. Okay.
So all these glasses are doing are blocking the green part, and we can see the red one.
That's right. And that's why if you put it on the boring diamond, you don't see anything because it's not emitting any red.
Yeah.
And so that's actually the photoluminescence that we're looking at being emitted from the diamond, right? Now, this over here is actually our nitrogen vacancy microscope. I actually use this in my lab. The nice thing about that is I've got it on this little frame and I can mount it over anything. So I mount this over cryostats, for example. We have one that's going to go on top of a dilution fridge, look right down the middle at a microscope down the middle. What this is I have that same green laser right here. It's only 5 milliwatts in this case. All right, and so the laser goes across This is a dichroic mirror, which allows green light to pass but reflects red light. So not so different than the glasses. Now this is an objective, so you can collect light. And on this little stick here, I've got a nitrogen vacancy diamond. Now, even more than that, though, I also have a microwave amplifier, and it's on a resonator, so I can actually control the spin state of that. Now, as you have now seen, you pump it with green light and red light comes out, right? That's the point of the dichroic mirror. The red light comes back through. That's why we have an objective. And it bounces off and goes into this photodetector. So we're pumping with green and just detecting the amount of red that's coming out. Okay. Now, in addition to that, I have a magnet. I'm going to take that off actually at this moment so we can see what's happening at zero field. It is all actually controlled through. This is my Jupyter notebooks. It's all running through FPGA. So this is RF system on chip. So this is kind of the latest from Xilinx. It has.
Is it Kentex Vertex?
It is.
Field gateway array.
Yeah, it's different than Vertex.
It's a Vertex, right?
I don't think so. No, that's different. Now,
Sure, the slides, but I can't.
Anyway, so what this is doing is actually outputting microwaves into my amplifier and then detecting from the photodiode, right? And everything's on, all the controls are happening here. We're not doing actually fast pulsing in this case, but this actually has nanosecond resolution for pulsing and for collecting data. Now, so I actually removed this magnet. This is a neodymium magnet that quite powerful. Peter can probably see me moving it around from over here. But what I can do is run a frequency sweep of optically detected magnetic resonance. And I'm running a little bit of averaging here, so it's going to take a second to repopulate. But what we'll see is basically the zero field spectrum pop up. This is a bit of a sloppy one that was in field. And because I'm having an eye-safe laser, we have to average a little bit longer. You give me a couple watts and this will be done in...
So that's pick toggle, right?
Yeah, this is Kickdog, right. So all this is controlled by through Jupyter notebooks on for my controller. This is open source.
Oh, can I get one?
Yeah.
What is it? What is your dog?
Kickdog, defect arbitrary waveform generator.
Oh, it's dog. That's the it goes dog.
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 Here you go.
Thank you.
Yeah, man. Thank you. Everybody got it? So, and here we go. This is our zero field optically detected magnetic resonance as detected here. Now I'd go a little bit faster and we actually do this manipulation live, but again, we're hurting for signal and noise because for eye safety. But what happened is we're taking the amount of light coming out and driving the microwave frequency. Right, and as I said in my talk that at zero magnetic field there's a degeneracy between plus and minus 1, and it's at 2.87 gigahertz. Right, and it's exactly where you see this dip in fluorescence. Now, you also notice that I lied, and then it's more than one peak, because there's also a anisotropic zero field splitting as well. So not only do you have this D parameter, there's also a parameter that couples into the spin X and Y parameters and gives you a very small splitting between the plus and minus 1 state. All right. So this is kind of the starting point. We can then apply a magnetic field, and I suspect I'm not going to align it very well. And we'll see how many peaks we actually end up seeing. But what this does is then gives you a Zeeman interaction. So the magnetic field is going to be give you an energy splitting between the spin levels, and we'll update this again and see how well I aligned the magnet. Now, if you recall, the NV actually has multiple orientations in the crystal, right? And so when you apply a magnetic field, there's a symmetry broken, and so you can have multiple magnetic field dot product with the spin components.
So this is going to be looking at some large number of individual.
That's right. Yep.
So you're getting an average of all of
all
those
orientations. That's right. That's a good. And there we go. It's a little bit. A background, but we can see outer peaks, these peaks, these peaks. So there's 4 sets of peaks in there, right? And those are from each of the 4 different orientations, and slightly misaligned from each other. Now, the other thing that you can observe, and it's maybe not so easy to see here, but there's actually a set of 3 peaks in there as well. So I increase that scanning resolution. That's actually the hyperfine interaction that you can see from the nuclear spins. And that's actually particularly sharp with the nitrogen vacancy as compared to other defects. So I can also then move my magnet a bit closer. Let me run again and increase the splitting. All right. Now, as I said, this is there's 2 things I'm not doing. One is high power lasers. The other one is our pulse laser. So this is all continuous wave measurement. So we're just applying a laser, which will initialize in the ms equals 0 state, but also give you photoluminescence. And then we're driving the spins into another state when we're on resonance. Now, I'll show you some examples from the other measurements that we do, which this controller also does. If I had my pulse laser with me, then we would be doing Rabi oscillations and T1 measures. Of course, those take longer too because your statistics are down. Oh, and the field is so large we're even off screen. So the largest peak is out here now, and then we have the other 3 sets there. So effectively, by measuring these distances, you can directly calculate the magnetic field that you're seeing. Now, this is just a neodymium magnet, so of course the field is huge, right? The power of this is actually how sharp these peaks are. So the sharpness here, you can see small changes in magnetic field then. So you give it a bias magnetic field and then make small tweaks to that. And that's actually the DC sensing that you're doing. Not these large changes, but the smaller changes that you get from some other perturbation, such as devices.
So you try and get that, so you're like on the slope of this line with some bias, and then you're just going up and down that line like a small fraction.
That's right. That's right. That's one way to do rapid imaging is you can sit on the side of one. Instead of taking the whole spectrum, you can just look at the variations like that. That's the way to do the quick imaging. Instead of taking the full spectrum per picture, you just take one and look at the variation of intensity. That's right. So, in this we have, I had a student that actually, I had her, diagram out all the pulse sequences that were happening and integrate them into the Jupyter notebook here. And so, we have, for example, that's getting the readout window. Here's Rabi oscillations. I'm sorry, here's Rabi oscillations. So the pulse sequence here is for some amount of time, you have the microwave pulse. And then immediately after, you turn on the laser and read out during that time. Okay? You actually only read out for specific sections of the window because what's happening is as soon as you start pumping, you both get a signal, but you're also pumping back into ms equals 0 state at the same time. So there's a limited amount of time where it's useful. And then we take a baseline measurement at the end.
Why is the readout? Does it not start right after the play?
So the reason is because there's a slight offset within the FPGA for that. That's a very perceptive question. And so this is what a Rabi oscillation looks like. In this case, what's happening is this is a very short pulse or no pulse, right? So you're always in the ms equals 0 state in that case, the shortest time. Then as you put more microwave power in for longer duration, you're going through the Bloch sphere, going from 1 to 0, and then back around, okay? And we use this to calibrate what our pi over 2 pulse is. So what you want to know is how much does it take to get into the XY plane of your spin, or how much does it take to completely invert? Then you have this decay envelope here, and that's related to inhomogeneity in either your microwave drive or some other inhomogeneous magnetic field that cause decay. This is recoverable decay though, because this is just inhomogeneity.
So in the beginning part of the curve, it's rather smooth, but it becomes like more zigzaggy towards the end.
Yeah, it's a little bit noisier there. I don't know.
Oh, there's no particular.
Okay, so this is, and ideally we'd be running that in a day fitting. Well, so this is actually Ramsey. I don't know if I want to talk about Ramsey though. Because it's another way to get the spectrum. This is actually a Hahn echo sequence. So in this case, what you're doing is you've initialized your spins. You tip them into the XY plane. And because of inhomogeneity, they spread out, right? This is what we saw. But then you do a pi pulse, which flips them in the same field, then they coalesce again at some time. With the NV, we then project them on the XY axis. And we actually even do a phase cycling, so you're projecting onto one axis than the other, and you can take a differential to get better signal noise that way. And then again, you have the same readout sequence here. All right. What that looks like is this is the T2 decay time. So this is the actual spin coherence time if you actually decouple from some noise. Right. Now, one thing that you will notice about this is it's not a very good decay, right? You see some wiggles in there, right? You guys remember what I also said about causes extra decoherence? The environment. This is actually, these dips are specifically at the gyromagnetic ratio of carbon in the lattice. So carbon-13s actually cause extra decoherence, what you would expect to be a nice envelope. Those are carbon causing extra decay. And if you actually take those delay times and convert it to the frequencies, you'd find the gyromagnetic ratio of carbon. So finally, I guess we can also measure T1 with this. And so what you do is you invert the spins completely with a pi pulse. All right, and then you wait some amount of time and then detect the polarization. That will tell you how fast those spins go back to equilibrium. And if we look at the results for this kind of thing, with the variable delay here, you just have a curve that relaxes like this. And so in this case, NV T1 is actually milliseconds at room temperature. So it's actually, even the electron spin takes milliseconds to decay. At 4 Kelvin, it's actually seconds, and very annoying to measure because it takes a long time to wait for it to decay. And so if you imagine that's the actual electron state, one of the powerful components of NVs from the quantum computation side is actually being able to address nuclear spins too. So electron spins are usually much faster than nuclear spins. Nuclear spins can last their states for seconds, even at room temperature.
Is that the reason why, I think towards the beginning of your talk, you said nuclear spins can be used as memory? That's
right. That's why they're the quantum memory. It takes longer to initialize their state, but they last for a lot longer too. And electrons are much quicker to manipulate as well. So that's why they're more like the processor. Electrons, the gyromagnetic ratio of an electron versus a nuclear spin is about a factor of 1,000 different. And so similarly, that's actually proportional to the amount of microwave or RF power that it takes to tip them in the same amount of time. So it takes a lot longer to control a nuclear spin to actually manipulate those. I mean, it's going to be in a useful way, but I've seen people addressing about 7 different carbon-13s with the same NV, and that you can use as basically a 7-bit register in that regard. Now,
What's the coupling that lets you flip the nuclear spin? Is that just like a hyperfine?
Hyperfine, and I don't know that it's dipole-dipole-like interaction if it's too far, but I think the best is going to be direct hyperfine. Yeah, and actually, I showed the triplet of the ODMR that you could see that if you actually go to high enough field, you hyperpolarize the nuclear spins too, and those triplets actually just become single peaks. Yeah, these little triplets will become single peaks because even the high hyperfine interaction, you get probably some sort of Overhauser mystery field that will saturate the nitrogen spins too, and also give you good initialization of the nitrogen spins. Yeah.
So you're talking about just like a high DC field, polarized nuclear. People, it sounds sort of familiar to the old gallium arsenide dot work, where they can basically, can you pump
Right.
nuclear spins to polarize them, and then
That's right. Well, so you are optically pumping the NV, right? So that's how you polarize the nuclear spin too. Is you're pumping the NV into ms equals 0, and that also allows you to pump the nuclear spin and give a polarization there. Eventually, I showed the plot where you have the magnetic resonance going in different directions for plus or minus 1. You get an intersystem crossing as well with the nitrogen if you hit the right field, because the nitrogen will have a magnetic resonance that goes up. The electron has magnetic resonance that goes down, and you can actually have them at very similar energy levels.